The European Space Agency has just published the first results from its mission to explore the origins of the universe, Planck. These results, known as the Early Release Compact Source Catalogue, focus on the coldest objects in the universe, from within our galaxy to the distant reaches of space. To detect these objects, Planck's instruments need to be extremely sensitive and cooled to the incredibly low temperature of 1/10 of a degree above absolute zero.
In centigrade, it's approximately 273 degrees below 0 degrees centigrade. We need these detectors to be very cold, because if they were not this cold, they would be overwhelmed by their own heat and they would not be able to detect the very cold objects that we're trying to detect.
Launched in May 2009, the Planck Satellite is located some 1.8 million kilometers from Earth, where unwanted emissions from Earth, the Moon and the Sun can be avoided. In constant rotation, it's able to survey the entire sky at millimeter and sub-millimeter wavelengths. Visible light telescopes see little more than the tapestry of galaxies around us, but by making the measurements at wavelengths between the infrared and radio, Planck is able to work back in time and show us the history of the universe from the first light ever produced. These fossil radiations resulting from the Big Bang are called the cosmic microwave background.
The cosmic microwave background is the first light that was emitted by our universe. It was emitted about 380,000 years after the Big Bang, more or less.
The study of these waves is essential to understanding the formation of matter and its origin.
When we look at the early universe with the CMB, with the cosmic microwave background, we see that it is almost featureless. It has no structure whatsoever. So we know that between then and now there has been an evolution. And we have simulated that evolution, which happens mainly through the work of dark matter. Dark matter is basically smooth when it starts out in the early universe, and it starts by gravity to clump into filaments and in a kind of spider-like network of structures. And the densest points of these structures is where the galaxies will form. Galaxies made of normal matter, the matter that we know and which emits light. So we can only see the small fraction of the universe where galaxies form, stars form and emit light. But most of the matter is in these huge filaments and structures of dark matter.
There are many other celestial objects that radiate at the same wavelengths as the microwave background. By detecting these with unprecedented accuracy, Planck enables scientists to subtract this data from the relevant data, giving us a much clearer picture of the microwave background.
The interesting thing about Planck is that it carries two instruments on board, and these two instruments allow it to span a very wide range of frequencies. That means, if you like, colors. So it is observing a wide color spectrum. This color spectrum goes from the long, what we call radio waves, to very short, what we call far infrared. We need this very wide frequency range because the microwave background is radiating only in the middle, but there are a lot of other objects radiating there too. And so we use the two extremes of colors to try to remove all of the radiation that comes from unwanted sources, parasitic radiation, if you like. There's radiation coming from our own galaxy, but also radiation coming from other galaxies and from clusters of galaxies.
So Planck.
These other compact sources have been presented in the Early Release Compact Source Catalogue as interesting objects in their own right. For example, it contains important new evidence for an otherwise invisible population of galaxies shrouded in dust billions of years in the past. Measurements of this population have never been made at these wavelengths before. Thanks to Planck's onboard detectors, scientists have been able to count some 189 galaxy clusters, 20 of which were previously unknown.
Ce qui est le plus intéressant d'un point de vue des amas de galaxies, c'est qu'en fait,
what's most interesting is that these galaxy clusters are like an intermediary stage between the very beginnings of the universe, which you see in the fossil radiations, and a phase much nearer to
on le
us.
voit avec le rayonnement fossile, et une phase beaucoup plus proche de nous, je dirais. Les amas sont, je dirais,
The clusters are an interface. They represent an intermediate phase which enables us to better understand, by looking at their formation, traces of the very first cosmic disturbances, back when the universe was just a baby.
Des traces de ce qu'était l'univers quand il était vraiment bébé.
Planck could also shed light on a controversy amongst scientists, the expansion of the universe, which is thought to have started immediately after the Big Bang.
Can we provide, if not proof, at least very good evidence that inflation really happened? So far, we've only known it as a mathematical idea. If we can show that it happened, can we somehow constrain how exactly it happened? What kind of inflation took place? These are the questions that we would like to answer.
While data from the Planck early release compact source catalogue is already allowing scientific discovery to take giant leaps, the final data release scheduled for January 2013 will reveal the full picture of the cosmic microwave background in unprecedented detail.